Hey there, peeps. We're taking a look at uniform circular motion. Okay, let's start off by looking back at acceleration, the concept of acceleration. So here we go. Acceleration is the change in velocity over change in time. V final minus V naught over delta t. Okay, so what happens here is that both velocity and acceleration are vectors, and therefore they're made up of both magnitude and direction. And so acceleration occurs when velocity changes magnitude. Okay, so that means that the motion of an object either speeds up or slows down. That much we know. But also, and more subtle, is that when velocity changes direction, it also implies that an acceleration has occurred. Motion turns, diverts from the straight path. So anything that changes from the Newton's first law basic motion of straight line, constant velocity, means that an acceleration has occurred. Why? Because a net force, must have caused the change in either speed or direction. Okay, so that's kind of important here as we look at circular motion, because circular motion involves constantly changing direction. So with uniform circular motion, there's a continuous change at the same rate of direction. It might be moving at what's called the same tangential velocity, the same speed around the circle. So the speed's the same, which is interesting. There's still acceleration occurring because there's a constant change in direction. So our definition of acceleration has always been there, but now we're really focusing on the fact that changing direction is absolutely an acceleration. So here we've got clockwise direction, and here's the radius from the center of the circle. And V tangential is defined as the vector, or in this case the velocity vector, that is perpendicular to the radius. So this red vector over here is perpendicular to the radius. This red vector here is perpendicular to the radius. That is the tangential velocity. So we're not to confuse tangential with the word tangent in trigonometry. That has a completely different meaning, tangent being sine over cosine, or opposite over adjacent, depending on how you're looking at it. But this tangential, or tangent vector, is totally defined as the vector that is perpendicular to the radius. So same word, but different mathematical definition. Here's how we're applying it. We can also consider, since we know something about angular motion, that the angular velocity omega is constant, so that the rotations are periodic. Okay, so we're not actually changing the rate of rotation from one value to another. There's no alpha. Therefore, the circular motion over here is occurring at constant omega, so that the time it takes to go one revolution is constant the whole way through. Okay, so that's really important with the uniform circular motion. That's where the uniform part comes in, that we're going to have some periodic motion as well, meaning that it repeats one full revolution at the same time. All right, whoa, yeah. Now that we know something about uniform circular motion, let's take a look at what causes it. It happens to be something known as a centripetal force. It's required because a force has to interact with the object to change its direction. And of course, uniform circular motion is all about changing direction continuously through the cycle of motion. Not to be confused with the term centrifugal farce. I call it a farce because it doesn't exist, at least in the frame of reference that is fixed, which is considerably, we usually call that Earth's frame of reference. And a centrifugal, quote, force will throw you to the outside of the circle. So it's a fictitious force that seems to throw you to the outside of the circle, which doesn't really make any sense if you really think about it, especially in terms of the fixed frame of reference. What does exist is the centripetal force. Centripetal literally means center seeking, so that the force seeks the center to correct the path each time. Like, watch this. Here is a clockwise motion. So we've got an object here. At this moment, the tangential velocity is right here, the red vector. And a centripetal force is something that constantly pulls this object into the center of the circle. So it's veering its path away from the Newton's first law basic type of motion, which is constant velocity in a straight line. This object would rather follow this straight line path right here at this moment if it were not for a force that's pulling it downwards in here. So it wants to go straight. The centripetal force says no, back into the circle. Later on, it wants to go straight, and again, the centripetal force says no, back into the circle. So that vector always points towards the center circle, the radius over here, and it's constantly diverted from this straight line motion, fitting the pattern of a circle. So that's how it works. So what are some of the physical forces that can cause this centripetal force? Okay, well, to create a centripetal force, you can have tension, for example. So a string or a rope pulling an object. So a yo-yo, for example, on a string, if you twirl it around, you'll see that it can go in the pattern of a circle, and therefore tension can create a centripetal force. Friction can cause a centripetal force. In fact, if it weren't for friction, we wouldn't be able to not only drive cars, but turn at all. In order to turn a car and take a right turn, left turn, you need friction actually creating a centripetal force, pointing to the center of that curve to keep you in that curve. If there's not enough friction, then you spin out. Actually, you will veer away and skid out of the curve. So it's really important that friction is able to create the centripetal force as well, and it depends on the value of mu static. The higher the mu static, the tighter a turn you can make, and the faster a turn you can make. The normal force, as it turns out, so roller coasters, for example, your washing machine, when you throw clothes in and it spins around, or the dryer, anything that has a wall that can push some object into the center, that force is the normal force, because the normal force is the Newton's third law response to an object that's pushing on it, and it could constantly, the walls of something can constantly push towards the center. And then we have universal gravitation. So satellites and planets are held together in circular orbits, approximately circular. It's actually elliptical, but close enough for the studies that we're going to do. So, for example, the moon is rotating around the Earth. It is orbiting the Earth. Why? Because there's a connection gravitationally. And the moon would rather careen in a straight line away from the Earth, but it's held there by universal gravitation, the gravitational force. So it undergoes this constant change in direction, keeping it in the orbit around the Earth. Any satellite will also behave in this way. The satellites that we launch, the International Space Station, etc., and the Earth around the Sun, quite the same as well. All right, so these are for physical forces, actual forces that create a centripetal force, and also can create this thing called uniform circular motion, so long as the v tangential is, the speed is constant, so the magnitude is constant, but the direction constantly changes. All right, that's good for this one. More ad. Out.